Good morning, folks. Wherever you are and where whatever weather you may be having, we will be having a reasonably sunny day today, followed by rain and then intense rain. And every time they have rain now, it's an atmospheric river, it feels like. It's probably not, but I think that's what they call it, just to make sure. Anyways, be aware. Rain on the forecast, and it's going to be fairly hefty. Um, Well, at least in this area. If you may be somewhere else, and then maybe you're in Hawaii and there's no rain. Well, there's always rain in Hawaii. Well, whatever. Anyways, hope it's nice where you are. We are going to continue talking about thermal expansion, which I think we left off with last time, and a couple of updates. So PLC 2 is due this week. Now you have the benefit of being an online class. So even though Friday campus is closed, it turns out the internet's open. So you can have till Friday to complete your PLC 2. Like I said last time, the number of things has gone up, but each one's a small little question. So it's like very quick for each little one. So hopefully take you about the right time. Work through that. And if you haven't completed PLC 1 and haven't turned things in, I'm going to encourage you again, do that so that we can make sure that you're going to be successful in the class, because an online class, you get behind a little bit and all of a sudden it turns out I don't really slow down that much. So uh, pace is going to be basically the same most of the way, as far as I can tell. But anyways, please turn things in. Lab 1 was due yesterday. So thanks to those of you who turned in Lab 1. We'll do Lab 2 later this week and get that up. What else is coming up? We have a homework today. Homework 1 is due today by midnight. So please make sure to turn that in. And quiz 1 is up and running. So if you've completed homework 1 and you're feeling good, you got I think I gave you an hour. Should be plenty of time. It is an open notes and open book quiz. So please, but it's closed everything else. I'm trying to um, I'm trying to encourage that you go ahead and use the materials so that you can use what you've constructed for this class. But please don't talk to other folks. Please don't use the internet. We are on the honor system, of course. So please try to do the best job that you can, so that it's an honest reflection of where you're at in the class. And let's see, anything else? I don't recall if there's anything else I wanted to say in terms of administration. We are off and running. And I will get things worked out and graded and turned back. So hopefully we'll be ready to get moving even further down the road. So we talked about thermal expansion last time. We're going to continue that. And the 1D case. We were talking about thermal expansion in one dimension, such that it kind of like this pen, the maybe the cross-sectional area, the extent of the object height-wise is small compared to the extent of the object width-wise, or maybe length-wise would be better. Okay, so because we talked about the reason for the expansion, that that each, say, atom or molecule or whatever is going to take up a little bit more space, so that the expansion depends on the extent in that direction. But if we consider something that's longer this direction, you're going to expect more expansion that direction. If it's small this way, you're only going to expect a small amount this way. And so that's why when you're talking about thermal expansion, we often call it in one dimension, right? It's linear because we are doing exactly this. We are assuming that the size dimension this way is small compared to the size dimension this way, and therefore we're just calculating this. And I came up with a expression for the amount of expansion that happens where I have a bar, say my pen here, okay, it's got an initial length of L naught, like that, and then, well, and this is at temperature T, and then when you're at temperature T plus a little bit, right, I'm going to raise the temperature up slightly, and I'm going to say, all right, now what happens? We're going to take a look at the length. If I, like I did in class yesterday, if I fix the left-hand side, then I expect expansion only this way. So we're going to say this goes to L naught, which is here. But now it's expanded out just a little bit extra, right? So there's L naught, and then this part here is the delta L. And like I said, yes, it has probably also expanded this way, but we are ignoring that for right now. That amount of expansion is then calculable by this, where the alpha is a material dependent coefficient. And the delta T is the temperature change. Since it is a delta, remember we could use centigrade or Kelvin. That will be interchangeable. So this is what we have. We've got that. I could take a minute to tell you a little bit about what happens if it's 2D expansion or 3D expansion. You can just take this idea and kind of run with it a little bit. Okay, so you could say in 2D, maybe I have a rectangle. Maybe I'm thinking of this as a bit more of a rectangular sheet of metal or something like that, where it's got a significant dimension height-wise, and it's comparable. That dimension is comparable to the length of the thing, right? All right. So if I were to calculate the area of this, you already know the area of this would be L times W. Okay. And if I expanded it, then each dimension expands. I'm going to once again pick the left side to be fixed. So possibly at temperature T plus delta T, it now starts to creep up this way a little bit and creep out this way a little bit, like that. So now this is all extra area, right? You might call that a delta A. Right? And that occurs at T plus delta T when I pull the temperature up a little bit and it starts to grow this way as well as growing this way. You can certainly calculate that if you wanted to ask what is the new area. Let's see here. If I wanted to say what's the new area, I would say that this A plus delta A, right, is the area here. This is area A, and that's area delta A. So A plus delta A would then be equal to the original area plus basically a expression in which
you have expanded both the length and the width, right? So let's do it this way. Let's actually do it this way. But this is actually going to be nu L times nu W, which is going to be L naught times 1 plus alpha delta T, right? So now my nu L, this distance here being delta L, and this distance here being delta W, like that. So if I have an original length, then I'm going to have an L naught times 1, which it was originally, or I called it L. Let me call them naughts so that we know these are the original lengths and original widths. I'm going to have an L naught times 1, which gives me the original area, or where it's going to, plus the expanded bit. I'm going to multiply that by W naught times the same thing. Now I'm going to assume something here. I'm going to assume that I'm going to write off the edge of what you can see if I'm not careful. So let's do this. 1 plus alpha delta T. Just squeezed on, barely good. So I'm assuming something. Now this alpha and this alpha are the same in the way I've done it. And because of that, this material has a name. Because same alpha in both directions. That does not have to be the case. This is known as an isotropic material. That doesn't have to be the case. It just simplifies our life a little bit. And honestly, I don't think we need to worry too much about having a different one in these other directions. You can certainly investigate that on your own if you'd like. If we go back and take a look now at what happens, this is now no longer in 1D, it's in 2D. Okay. If we now take a look at just blowing this thing out a little bit, what we're going to find is that A plus delta A is now L naught, right? This original piece here times this original piece here. So that's the original area like we would have expected. Okay, and now if I take these two parentheses terms and I FOIL those things out, and I interestingly ran across somebody who didn't know what FOIL was. Well, anyway, I multiply what's in the parentheses. So I'm going to get 1 plus, and I'm going to get 2 of those things now. And then I'm going to get a squared term here on the end. And this right here, the alpha squared. We're saying, look, alpha is what? It's around 10 to the minus 6. Remember, its units are per centigrade. Okay. Its units are per centigrade, so this is an order of 10 to the minus 6. And therefore, this thing is a million times smaller than this one. So we're going to ignore this. Right? So basically, the area expansion in 2 dimensions then is L naught W naught, and that's the original area, right? Is area plus this thing here, in which 2 alpha is basically the area expansion coefficient. Plus area times. There isn't necessarily a name for that. We just call it 2 alpha times delta T. And your new the added on bit, your new expanded piece to this is then just this piece right here, which kind of is nice because then it's just kind of like a linear one, but with a slightly different coefficient. And that's especially nice because the coefficient is the area. I'm sorry, it's like the dimension number, right? And if this were volume, this would have been a 3. as long as the material is isotropic. So it works out kind of nicely. All right, let's do a quick example here with back to linear expansion. Okay, back to linear. Let's do a quick example of heating something. And actually, I'll show you the setup first, which I have over here. And what we have, this is not exactly the problem that we're going to do, but it's essentially close to it. What I have here is this is a brass ring on a nice thermally insulated handle, and you'll see why in a minute. And here is a brass ball on a also thermally insulated handle. And what I'm going to do is we're going to pass the ball through the ring, right? Let me show you this way. Fits really nicely. Okay. And now, put this here for a minute. And now, it's a great day because we get to play with fire. I'm going to heat this thing up. I'm going to heat the ball up, which is going to cause a volume expansion. Okay. But that coefficient is probably 3 times what the linear expansion coefficient is based on that analysis. Let's see how we're doing here. Heating it up. This takes quite a bit because remember the coefficients are fairly tiny, right? These are numbers on the order of millionths, 10 to the minus 6th. So not quick, right? And we'll put this down. Okay, now we've got a nice hot, and you can see it doesn't fit. Not fitting. Still pretty warm. How do I know that? We'll talk about convection a little bit later today, maybe. But your nose and lips are very sensitive to heat, so just holding it close. We'll get to the point. It's slowly shrinking. Oh, look at this. Got this on top now. It's right over it. And give it a few wiggles. I can just about get through. There it goes. Right? There it goes. Now it's lost. It's cooled off. Its temperature has dropped to the point where now, there it goes. Nice and easy. Riveting. They used to, or maybe they still do, rivet bridges. This is the opposite of what you would want in a rivet. What you would want to do is heat this thing such that it expands, goes over this thing, and then cools. And now, since these two things, it cinches around, and now since these two things are in thermal contact, you can't heat one without heating the other. Kind of cool. And then so they'll stay basically put together, and you can't get them apart. So nifty. All right. Ooh, this thing's still pretty warm. Let's put that somewhere where it's not going to start a fire. Got something else here for you. Got something else here for you. Those of you who have an old style thermostat, I didn't bring it with me, but it's one of those rotary ones. It has a piece of metal in it, which is a really interesting piece of metal. It's called the bimetallic strip, and this right here is one of them. What it is essentially it's one type of metal on this surface and a different type of metal sandwiched on like an ice cream sandwich, like this.
except it's got no ice cream. So it's not really that fun. Yeah. I think it's something better than that. So that when the temperature changes, one of them expands at a slightly different rate than the other. Hmm? Pretty groovy, huh? How about that? That down for a minute. Just keep an eye on that. As it cools off, back it goes. Great, huh? Also, if you're interested in materials, which pretty cool if you are, go Google the material called nitinol. That's a memory. It's called a memory metal, nitinol. Nitinol. Nitinol, because it's a compound of nickel and titanium. What they do is you can bend it into a shape, um, cool it off, and then once it's at room temperature, right? You do that while it's hot, cool it off, and it stays in that shape, and then it's at room temperature, and now you just bend it into some other form, and then you heat it back up, and it goes right back to where it was. Really cool.
Memory. It's a memory metal. Pretty nifty. It's I don't know where that compares to memory foam. I don't know. Anyways, let's take a quick example here of linear expansion. Give a quick example of linear expansion here. What I want to do is think about that exact situation that I just did with the ball and the ring. Except I'm going to be a little bit different with it. Oops. Yeah, sorry about that. I'm going to take a brass ring, same idea. And now instead of having a brass ball, I'm going to do with a steel ball or say a steel rod. Something where I can concentrate on the linearity of the diameter expanding. Okay. So an example would be like this. Okay, I've got a brass ring, and the ring has an inside diameter. Okay, so that would be this one here. I'll call that D of the brass. I'm going to take the steel rod, and the steel rod has an initial also diameter in which it's just slightly too large to fit in. Right? So my steel rod is maybe this big. This is made of steel, and now I've got the outside diameter of this. Call that D of steel. It's just a little bit too big to fit in though. Okay. So what we're going to count on is being able to, and what we're going to do is we're going to heat both of them up. Okay. So what we're going to count on is that the steel does not expand at the rate that the brass does. In other words, we're going to heat both. Say they both start at room temperature. Okay. And we're going to put them both in an oven, right? And they're both going to expand. And then I want to know what temperature should I heat them to such that I can fit the ring onto the rod. Okay. Heat both until okay. We'll start with an initial temperature, say room temperature, we'll call it initial temp of T naught. They both are at that temperature. Now, in order for that to happen, alpha of the brass, I'll tell you these numbers. I looked these up. Alpha of brass is 19. Not that this really matters at this point in time, but just to give you a conception as to why this is going to work. Alpha of the steel is 11 per centigrade, right? Or 11 times 10 to the minus 6. So as I heat these two things up, they don't expand at the same rate. The steel is slowly, but the brass is a little bit quicker, a little bit quicker, a little bit quicker, a little bit quicker. So ultimately, this thing will grow at a slightly quicker rate than this will, and then there will be a common temperature. Since we're starting this one slightly smaller than this one, there'll be a common temperature at which the hole in the brass ring will slip nice and snugly right over the steel rod. So the question is, what's that temperature? Find the final temperature where this happens. Ready? Okay. Well, this is not quite what we're looking for, but it kind of is. Okay. So what we ultimately want to do is find the point at which D of the steel is equal to D of the brass. That's what we're looking to have happen. Okay. They both are going to undergo the same temperature change. So if I were to write this at whatever temperature this is happening at, what has happened in order to make this true is that D of the steel, this would be at the final temperature. Now, in order to get to that, I had to have done D steel as it sits here and said, okay, D of the steel has expanded, 1 plus alpha of the steel times delta T. And I'm going to set that equal to D of the brass times 1 plus alpha of brass times delta T. And those delta T's should be the same. Okay. We're starting them both at room temperature, and we're, like I said, we're putting them both in an oven. All righty. So what we're going to do here, my goal is to try and solve for the delta T. That'll tell us how much I had to increase the temperature. And then all I have to do is add back on the original T naught, and I'll find what the final temperature is going to be. What do I need to set my oven to, in other words? Okay. All right, so at this point, what we want to do is solve for delta T. All right, well, that means that I'm gonna have to plow these things through here. And I'm gonna note that one of them is gonna be slightly larger than another. So I'm gonna probably take the idea of the brass as since it had a slightly smaller diameter, I'm gonna take that as probably being the smaller one, and I'll just use the steel as the big one. So I'll take this, move it over there, and then take this and move it over here. So what we should have over on this side is delta T multiplied by, right? I'm going to have D steel times alpha steel. And I'm going to take this term over there. I'm going to have minus D brass times alpha brass. That should equal then this term that comes over here, which is D brass minus D steel. Which means that this is probably the wrong way to have done it because that's going to be initially a negative number, right?
Steel is greater than brass. So, okay, so I got it backwards. Well, let's flip them around then. Solve for delta T. If I just multiply both sides by a negative, I'll have steel minus brass divided by, and I'm going to flip these around. So now I've got alpha brass D brass minus alpha steel D steel, like so. All right, and that, as I said, is how you calculate the temperature change in that needs to be affected. Now, in order to find the actual temperature, I want to find this final temperature, I'm going to need to add back on the T naught. So then T final is going to be T naught plus this thing. Right? And that would be how you could calculate this. I gave you initially these two numbers in order to try and motivate why, when I'm bringing them both to the same temperature, they will eventually fit. Okay. Let's start with, all I really need is the diameters. Let's start with the diameter. If we just plug a few numbers in here, let's start with the diameter of the steel as being, say, 3 centimeters, and the D of the brass being slightly under that. Let's call it 2.992 centimeters.
All right, so this is 3. I should pay 3.000. All right, so we paid a machinist a lot of money to make these things because the tolerances are a tenth of a millimeter. Or no, that's even worse than that. It's a thousandth of a millimeter. Is that right? That's a millimeter. No, that's a tenth. So hundredth of a millimeter. Yeah, pretty tight. That's pretty tight. So if I put these things in here, I'm going to find that this delta T here turns out to be about 300. What did I get? I got 345. So if I start with initial temperature of 25 centigrade, say, plus all of that times all of this and all that stuff on the bottom, I get that my final temperature is 360 centigrades. That's where I came out with. All righty. And that's basically how you can use uh, that's how you can use thermal expansion to uh, to show a few things. Now, I did. Let me just let me see real quick. I have some pictures, so let me just see if I can quickly find what I did with those. On a minute. Ah, here we go.
Okay, let's see if I can do this. And let's get rid of that. And let me see if I can share my screen here so you can see what I'm looking at.
Okay. So I got some pictures here, and um, I will be honest about this. Um, these are not. I'm. I put these together for the conceptual physics class, and it is a little bit of a lie that these railroad tracks all buckle due to thermal expansion on a hot day. That's actually not totally true. Um, but nevertheless, it's pretty impressive. And I think that's the key here to remember that it's impressive and not that I'm lying about it. Now, why do railroad tracks buckle during hot days? Well, if you if you've ever rode the train or you ever watched a movie with a train in it, then what you would hear as the train moves is ka-ting, 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 right? Because what they did was the wheels of the train is rolling over little gaps, right? There's a gap in the railroad. Why is there a gap in the railroad? Well, now you know. Because when it gets hot, the rails expand and they fill this space in. So it gets hotter, 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 and they fill the gap in because the entire thing's expanding, right? And it's filling in this gap. So someone who's really smart eventually waited until the hottest possible day, and then they welded all the tracks together so you didn't have to hear that pesky which is great until it actually becomes hotter. And then what happens is you get these two things pressing against each other, and then they go like this. And you can see that pretty well in the second picture. Oh, you can't see me pointing. I'm just going to point at you. You can see that in the second picture, where there's a pretty nice. What we're looking for is something that's gone like this, right? Like that. In the second picture, that's pretty. Um, I don't know, clear. So, but in the first picture, yeah, it's not exactly the same thing. They've warped and deformed maybe. And you can see the same thing in the third picture. There's a one of these going on. I don't think that's due to thermal expansion. I think that's actually due to some type of soil shifting or strike slip shifting or something like that that's going on. I don't think that's thermal expansion. Maybe I'm wrong, but number two, I'm pretty sure is. Anyway, so there's that, and I was going to show you these other ones too, because look, this happens to things that we build, like big things that we build. We have to build in, if you're going to engineer stuff, you have to build in tolerances for when the temperature of the environment is changing, right? So what I was telling you, I think yesterday, was that the temperature of the Golden Gate Bridge can really change the length of it by quite a bit. So let's take a look at the next one here. Where's my? Yeah, here we go. Oops. Okay. And because of that, structures are inherently weak at these joints. Okay, so here's a situation where levees are created and they are big concrete slabs, but they have to leave room for the concrete slabs to expand. That means they leave a gap such that the concrete can expand into the gap. But if it's trying to protect water from coming through, then you have to put a membrane there and seal it up with something. And that's inherently weaker than the actual concrete. So that uh, when a an unforeseen large event comes along, like a hurricane, and this is what happened to Katrina in New Orleans in '05, was it? The levees couldn't take they were really in bad shape as it was. So a catastrophic event like a huge hurricane coming in and the amount of water that the levees had to try and deal with just wasn't happening. Okay, so here I've got a picture of someone inspecting. They have people inspecting the levee um, expansion joints in order to make sure that they're sealed properly for when a really bad thing happens. And speaking of other bad things happening, here you go. Look at this. Every time you drive over a bridge, you see uh, that picture in the bottom right. You see these things, right? It's called a finger joint because basically what happens is the bridge is cold and then it warms up and it again closes into the gap, right? And you see these things every time you drive over a bridge. Of course, when there's a big catastrophic event, and I forget the engineering term for this. It's not something like it's overloaded or I can't think of it. But anyways, when something like this happens, note the picture on the top left. See how clean that thing fell? Guess why? Well, it was at one of those expansion joints because it's right weaker. So they're going to fail at those points rather than in the middle of a big slab of reinforced concrete. They're going to fail at these points. So a large piece of civil engineering is trying to figure out how do I make a structure that's big be fairly rigid and still leave room for it to expand and contract as the temperature of the surroundings changes. Um, so there's that. Let's see. Is that enough? Yeah, that's enough. Oh, actually, that's cool. I'll just point this out. Um, this linear expansion is in general a rule, but of course we have an exception. So good. I'm glad I clicked on that one because I forgot to mention this. Um, Liquid water thermally expands as it increases its temperature, just like you'd expect. And it also contracts as you decrease the temperature, just as you expect, right? The reverse of linear expansion is linear contraction. If you cool it off, it gets littler. Except when you get to this particular temperature. At 4 centigrade, water, if you continue to cool the water stops contracting and it actually starts expanding again. And so what happens, as you can see here, that little curve in the density of water means that when it's at 4 centigrade, it has contracted as much as it possibly can, which causes the density to be as high as it possibly can. And then after 4 centigrade, it starts expanding again, which lowers the density. And this is good for life on Earth, as it turns out. We probably would not survive if this wasn't the case. We probably would not have survived as a species. I'm not an evolutionary biologist, but I do know that we basically evolved from pond scum. And what's more than that is that most liquids will float on top of the same solid, right? But in water, that's opposite. It's the solid that floats on the liquid. And it's because of this that lakes freeze on the top rather than on the bottom. Like every other material, if you have a solid and a liquid of it, the solid drops into the liquid and sinks. But water's opposite, and this is why. So that when the ice covering occurs at the top of the lake, if it's a really deep lake, only the top will freeze. The bottom will still be at 4 centigrade because that's the most dense water and stuff can still live in that environment. If that lake was freezing from the bottom upwards, then it would have frozen, probably killed off all of the pond scum that we evolved from, and then no life. So there you go. Your happy to be alive moment of the day. All righty. So good. Hope you enjoyed that. You're alive because water expands as it becomes a solid. And you knew that anyway, because ice floats on water, on liquid. And you've probably seen all these horror shots of people who with water pipes that have frozen, like in Colorado or something like that, where the water pipe wasn't insulated properly, and then it temperature dropped so much that it ruptured the pipe. And there's not a whole lot you can do about that. Water, when it's doing that, it really is, it's not going to take no for an answer. So you can try and stop it, but it's pretty insistent. when it freezes, when it gets down below 4 centigrade and it starts to freeze like this, it's pretty insistent that it expands. So that's the exception. You can kind of call that a negative. Yeah, right. They should have. But you can kind of think of that as a negative expansion coefficient, if you like, because as the temperature is going down, the thing's expanding rather than temperature going down, thing contracting. There are some engineered materials. Also, another little Google search will reveal that negative coefficient of expansion. We've made some water. I think I should probably know this, but I don't. I think water is the only naturally occurring material that does this. Um, so I'll go on record as saying that. I know for sure that we have engineered materials to contract as the temperature goes up. But in terms of naturally occurring ones, I think it's only water. I can't think of any one other material whose solid floats in liquid right off the top of my head. So there you go. There's that. Okay. Let's talk now about, we've talked about, all right, so let's just real quick review. We've talked about the first law. Okay. Remember the first law as being our change in internal energy due to work done and heat transferred. Okay. So once again, when you think about drawing this on a PV diagram, right, the internal energy is a state variable, so those will be points on a PV diagram. The Q and W are not points, they're due to the path, right? So this is a really interesting equation from a mathematical perspective in some sense. Whereas I have two path-dependent quantities here adding together to give me a path-independent quantity. Kind of cool. Now, maybe just real quick, we'll just do an example of some first law reasoning to kind of sum up a little bit of what we've learned, and then we're going to go talk about how heat transfers. We'll do a little bit more of that. So let's do this. I have, let's see, I have here an initial point, and I have up here, I have a final. All right, so I want to find some different processes to take me from initial to final. I'm going to choose 3 different paths, and we're going to try and calculate some stuff. So here's one of the paths, goes there to point A, and across isobarically this way. Or I could choose the path that's the opposite of that, go isobarically at this point, along this path here to point B, and then up that way. And then what I'm going to do is I'm going to come back from final to initial along an arbitrary path. Perhaps it looks like this. And I'm going to go back that way. Okay. Okay. Now, let's do a little bit of first law reasoning. Okay. It doesn't, this shouldn't depend on what kind of system it is. All right. Let's just do a little bit of thermodynamic reasoning. Let's suppose that the heat that I transferred, Q, to go from I to F along the A path. So I'll call this IAF. Okay. Let's suppose that was 50 joules worth of heat. Along that path, same path, IAF. Okay. Let's suppose that I did 20, or the system did 20 joules of work, and that means it's negative work, right? I to A to F. Okay. Let's further suppose that if I went along the B path, okay, I went down here and up. Let's further suppose that if I went IBF, that was 36 joules worth of heat. And I'd like to see if we can find a few quantities here. Okay. let's take a look and see. First thing I want to find out is what is the work done along path IBF? If I then am at point F and I come back to point I along the arbitrary middle path here, right? What's if I suppose that I did work, suppose I looked at the work going from my final state down to my initial state down here, right? Suppose that that's 13 joules. Now I'd like to find what heat did I transfer if I went from final to initial that way. Find Q from F to I. I guess I should take if. Okay. If I look at the internal energy at point I, and I say the internal energy at point I is 10 joules, I'm interested in finding what's the internal energy at point F. Internal of F. Now suppose I went along path B, and I know that the internal energy along path B, I'm sorry, the internal energy at point B is 22 joules. I'm interested in finding the heat transferred between I to B. And after that, I'm interested in finding what the heat is transferred between B to F. Okay. This kind of reasoning, or this kind of problem solving, okay, hopefully should be fairly it should be a developing skill for you. All right. So what I'm going to do is I'm going to give you a couple of these answers and see you can work out some of these quantities and see if you are matching up with what I came up with. So I'll give you the answers to a couple of them. For example, I found that the work done from F to I was negative 43 joules. I'm sorry, the heat transferred from F to I was 43 joules and it left the system, transferred out. And let's say B to F, I'll give you this one too. I found 18 joules for this one. All right, so I'll give you those two answers. Just to make sure that you're on the same path, I think that you should be able to take care of these, see how you're doing. All right, so use this as a bit of a check just to see, okay, can I do a little bit of first law reasoning and find some numbers due to some processes from a PV graph? And if so, good. And if not, well, work on it and think about it until you can do it. Let me know if there's any questions. All right, oops, let's leave that. I'm going to take this off. And then we're going to go look at heat transferring. Which is the subject of lab this week. All right, so we've investigated each one of these quantities individually, right? We looked at the work. So work is a force pushing through a distance, and we can relate that as a pressure to a volume change. We've looked at the heat, and we have sensible heat, which is a temperature increase or decrease, say a temperature change if heat is transferred in or out of a system. We also talked about the latent heat, which is hidden because it contributes to a state change. So you would be looking at something that's going from, say, liquid to solid, or solid to liquid to gas, or something like that. And we've looked at the internal energies, especially from the perspective of the ideal gas, in which the ideal gas internal energy depends solely upon the temperature. Okay, and the consequences of that during the different processes, isobaric, isovolumetric, isothermal, and not quite yet super. We haven't quite yet looked in depth at the adiabatic process, but that also is one of those. Okay. So let's look a little bit more closely at how we transfer heat from one place to another. And looking a little bit more in depth at the Q term. Really, I guess I should. Well, this is a little bit egocentric here. How do we transfer heat? How does heat transfer? Would probably be a better question here. Nonetheless, there are essentially three modes for heat transfer. Okay. One here is called conduction. And this is basically the simplest thing. I take two things that are at different temperatures and I just put them right together, right? This is direct thermal contact. So air conducts because it's always in contact with us. At least I hope it's always in contact with us. If it's not, maybe call 911. Um, because you've been in water for too long. I don't know, or something worse, like not air. Yeah, well. Conduction, right? Putting it directly in contact with one another. We'll do an example of that in just a few minutes. Second one, though, now, oops. Second one here is known as convection. And this is a situation that occurs when there's a fluid involved and it involves bulk movement, bulk current movement of the fluid. Now, the reason for that is typically we can go back to the thermal expansion idea and say, okay, what if I have a hot object right here in air, or maybe it's in water or something like that? If I have a hot object and I submerge it in water, say, the water around this is going to start picking up some of the heat that's emitted from the object, right? The object's it's in contact with the hot object, so it's gonna conduct heat into the water that's surrounding it, or if you like, into the air surrounding it. All right, that's conduction. Typically, though, then what's going to happen is because this fluid is now at a higher temperature because heat has come into it, its density is smaller. And so it starts to rise. It starts to float above fluid that has greater density. Okay, so this is what's known as heat rises. It's not heat rising, it's hot air rising, or warmer water kind of swelling around. The lower density fluid is going to start to move upwards, and then from the bottom starts coming up the to fill that space comes the other fluid to then pick up some more of that heat, and then it starts to go up. So you get this kind of big thermal cell, and these are pretty common in the oceans and in the atmosphere. You get these thermal convection currents, right, that go up and down, and you'll normally see these. It's really nice to see these at a lake. If it's kind of a cooler morning and you'll see a lake, what will happen is the lake is typically slightly warmer than the ground. So the air above the lake will conduct some of that heat. Its density will lower and it will start rising. And the birds know this. Birds know this because they'll go right into that that warmer air that's rising, and they'll just kind of not have to flap a whole bunch, but you'll see them start to spiral, and all of a sudden they haven't seemed to expended any type of work, and their gravitational potential energy just went up. You see? It's energy for free. Birds are smarter than us. Okay. So convection is bulk fluid movement. And it's carrying it's carrying the extra energy with it. Okay. Bulk fluid movement that carries. I don't want to say it carries the heat because heat doesn't really get carried. It's the energy that gets carried. Last one here is radiation. We will investigate all three of these, but note that for conduction, you have to have something in contact with your hot or cold object. I'm just going to assume a hot object just to make it easy. So I've got a hot object. It's in air if we're down here on Earth, and therefore air will conduct heat away from it. Now, if I take it to outer space, no air, right? So no conduction. You basically kill this as soon as you take something and remove everything around it. Okay. Since there's no air in space, no convection because there's no bulk fluid. All right. So if you are in outer space, radiation is the thing that transfers heat. And of all three of these, this is definitely the slowest. Okay. So you'll often hear people say, well, if you go into outer space without a spacesuit, uh, you'll you'll freeze immediately and your blood will boil and you'll die within seconds. And that's all not true. It's not true at all. It will be painful. I'm not saying it's not going to be painful, but the rate at which heat is leaving your body means that you're not going to suffer hypothermia for like at least 12 to 14 hours or something like that. I'm pretty sure it's less than a day. Of course, in the meantime, you will have had other things happen. Um, but we won't go into those. Anyways, radiation. So radiation is literally electromagnetic radiation. And it happens all the time. It happens to everything that has a temperature above zero, and that's zero on the Kelvin scale, not the centigrade scale. So everything above zero radiates. Okay. And we'll see the consequence of having higher temperature means that the frequency of the electromagnetic radiation changes. Okay, so that's one reason the sun glows because it has a particular temperature effectively that we see on the outside of it. Earth also has a temperature, but we don't see it because it's not sun, and we can live on it because it's way cooler. Nonetheless, it radiates in the infrared rather than the visible. So that's radiation. Everything above zero radiates. And let's take a look at conduction to start us off. So I have here a one night there was an incursion to the Space Shuttle Center, and some of the space shuttle tiles were possibly liberated. And that's what we have here is a space shuttle heat shield tile. And you can see it's fairly light. It's not massive. It's actually um, it's quite easy to move around. But what I am going to do now is show you how well it conducts. Okay, so I've got my flame going here. Let's turn that down a bit. Okay, I got my flame going here. Now I'm not sure if you're going to be able to see this. Oh yeah, it shows up pretty well. So I'm just going to heat this area of the tile up a bit, or more than a bit. And you'll notice that I'm still holding it down here.
So this tells you something about the conduction. Okay. I think you can probably guess that this is I put a significant amount of heat into this, right? This is not an accident that it's glowing orange here. Okay. I'm just going to take the flame away. Okay. It was right here that I was putting the flame, and you'll notice that I can hold it all right around this without too much of a problem. In fact, if I just put my fingers right, oh, it's a little warm. Okay, now it's too warm. But that's kind of impressive for, I just had a direct flame on that point where my thumb is, and it's warm. I feel it. So let's talk a little bit about the specific heat of this, the specific heat. So I just dumped in a fairly large amount of heat to this thing, and its temperature did not go up that much. So it's seemingly got a fairly low specific heat, fairly highish specific heat. But not only that, let's talk about conduction, the properties of conduction of this thing, right? Even while the flame was on this thing, I could have my hand like right here, and that heat doesn't move very much. And that's essentially what conduction is. It's the ability of an object or a material to move heat around. You're a better conductor, you move heat easily. Okay? It's kind of the same thing heat-wise as with electrical. So if I have something that can move electricity easily, I typically will have something that can move can move heat easily. Okay? So if it conducts most things, right? Electricity, heat, possibly shock waves, things like this. If it's the opposite, and this is an insulator, it will not conduct anything very easily at all. And that's what this is. And this is why you use this on the space shuttle, because you want this between burning hot coming into the atmosphere and people. That's kind of the situation here. So these things can reach upwards of 1,000 centigrade. I think maybe even 1,200 centigrade on the incoming side, and the people in the cabin are just, well, at least this was when the space shuttle was operational. Just okay. So we'll talk quickly about conduction, and then it looks like we're just about going to be done with today, and tomorrow we'll talk about these two. Well, we'll finish up talking about conduction as well, and then we'll talk about these two. So conduction has to be direct thermal contact. So I'm just gonna use air because air is an easy one. Everything's in direct thermal contact with air, and you take a look at. For example, a window in which, so maybe I have a pane of glass here, okay, and it's got some thickness to it. Perhaps on this side, we're indoors, so maybe this is our indoor temperature, so maybe this is 20 centigrade. Maybe out here, this is our outdoor temperature. Well, we don't really get much of this. Maybe this is -5 centigrade or something like that. Okay. The air on the indoor side is warmer, causing the glass on the indoor side to warm up. The air on the outside is colder, causing the glass on this side to be colder, and therefore there's a temperature, what's called gradient, within the glass. The glass is now going to conduct heat from the indoor to the outdoor based on that temperature gradient. All right. And a gradient, if you're, I don't know when gradients come in, maybe 5C or something. So if you're not familiar with the gradient, it just means that there's a slope to the temperature, right? It's changing through the window, and the window is therefore able to conduct heat through it. Just as a quick example, let's suppose that I have like a hot bath over here. Maybe this is just water or something, I don't know. And I got a cold bath over here.
right? TH, T hot and T cold. And I'm going to connect these two hot and cold paths with a metal rod or something like that. Typically, when we talk about conductors, metals are the number one conductors. They are very good at electricity and heat. So you would talk about things like aluminum, copper, steel, brass. All these things are going to conduct reasonably well. Um, so that's the easy part here. Things like air and plastic and rubber and wood and things like that do not conduct. They are insulators. Okay. So suppose that I slice this thing up. Maybe it's got a circular cross section to it. Okay. But you can see that because there's heat here and I've connected it to there, it's in direct thermal contact. So heat is flowing that way. The heat flow means that there's a rate of heat transfer. If I just stand, suppose I'm standing right here and I'm looking and I'm saying, okay, I want to count how many joules of heat are going past. I do it per second kind of thing, right? I'm going to say, okay, in 1 second, I counted 1, 2, 3, 4, 5, 6, 7. 12 joules of energy went by. So this is really a rate. This heat flow is a rate. Okay, it's a rate of heat transfer, and it's basically dq dt. Right? The heat flow is dq dt. Now, if we've reached a steady state, then it doesn't matter where along the bar I look, I should have the same rate of heat flow everywhere in the steady state, and that's what we're going to concentrate on. We're not going to worry about starting and transient bits like that. But what I want to ask though, what variables, what physical parameters do you think the heat flow would depend on? How could I increase the heat flow? Okay, I'll give you an example. One of them would be maybe make a thicker bar, right? If it's like traffic, I could stand and watch traffic on highways going by, and I could say, well, if we increase the number of lanes, wouldn't that mean that more traffic could get through? Well, in theory, yes, but in practice, no. So we would say this is proportional to, for example, the area of cross section. Okay. It should also be proportional to what type of material. I just told you that wood, if I just had a wooden stick here, it's not going to do as well as a bar of copper. So it should also depend on the material, the conductivity of the material. Um, the temperature, if I suddenly made this 1 billion degrees and I kept this at room temperature, wouldn't you think that's going to transfer energy a lot quicker than if this was like a little bit above room temperature? So the difference in temperatures. The difference in temperature is also going to make a difference in how quickly heat's going to transfer. Um, so we'll start off with that. What I'm going to do is, and lastly, I will put in the last one, which is the length of the length of the rod. What we're going to do is we're going to take these into account and try to come up with a mathematical expression for this next time. And we'll do an example and we'll go through convection and radiation. And then this is Wednesday. So then on Thursday, that'll be our last class this week. And I apologize for the late record uploading yesterday as my computer battery died and then it decided it needed to reboot and reinstall something. So I had problems and Anyways, yesterday's video is up now. Today's video will be up in a little bit later today, but that won't bother you because by the time you're seeing this, it's already posted. So, good luck to you wherever you are, and I hope to see you again tomorrow. We'll continue talking about heat transfer, and we'll go through the other modes, and we'll go from there. All right. So until next time, folks, happy day.